Hi everyone, this is the last lesson for unit number 1. It's lesson 1.5, and it's on effective and equivalent interest rates. So if you remember, or if you've watched lesson 1.4, the end of the lesson showed you an example where you had the same amount of money at this compounded annually or monthly. And you saw that you could have a lower interest rate if it was compounded monthly and make the same amount of money as if you compounded annually at a higher interest rate. Okay, so the reason for that, if you remember way back to the start of this unit, compound interest means you earn interest on the interest you've already earned. Okay, so each time you have a compounding period, you earn interest. So then the next compounding period, you earn money on your investment, plus you earn money on the interest, okay? So in general, the more compounding periods you have, the more interest you will make. In other words, a lower interest rate, a lower nominal interest rate, but compounded more often will be the same as a higher nominal interest rate, okay? That's compounded less often. Okay, and that again comes down to the fact that each time it's compounded, you're earning interest. It's going into your bank account or into your account. And then for the next period, you've got more money in there, meaning you can earn additional interest, okay, on that interest you've already earned. And that all comes down to having more compounding periods. Okay, so the first item I want to look at, this is going to be one of your shorter lectures. It's only covering one section, 10.3 in your textbook. I want to look at effective interest rates. So what this means, okay, is if you're given an interest rate, let's say in my example I'm going to do it's 8%, what is it effectively worth in terms of interest, depending on how often it's compounded? Because again, you're earning a little bit more the more often it's compounded by earning interest on the interest you've already earned. The key term is, if you remember from your equation, future value is equal to present value times 1 plus the periodic interest rate to the exponent n. So this term, all right, this 1 plus I to the n is the most important term, because what that is it's a multiplier. Again, it's going to come out to something like 1.1 or 1.2 or maybe 1.005, something, okay? And since it's greater than 1, the higher that this multiplier is, the more your money is going to be worth in the future, right? Because that means the more interest you're earning in that period in time, okay? So that's the term when you're looking at effective interest rates. That's the piece of the equation that we need to look at, all right? And let's look at a few examples. So if you're earning 8% interest, and let's say, okay, I'm not even giving you a dollar amount. We're only going to look at the 1 plus I to the exponent n term. If it's compounded annually, all right, then that means that your interest rate, your J, is 8%, okay? Actually, I'm going to move this. J is 8% for all of them, okay? So what you do know is that J is 8% for each one of them, which is 0.08, okay? Or 8 divided by 100, moving the percentage sign, which is 0.08. So if it's compounded annually, again, we're looking at the 1 plus I to the exponent n term. J is 0.08. M is just 1 because it's compounded annually. So your periodic interest rate is 0.08 divided by 1, which is equal to 0.08. Your number of compounding periods, n, is equal to the number of years multiplied by the number of compounding periods per year. Now let's say in this case, I didn't write it in the question, but let's say this is compounded for a period of 1 year. All right? That means that n is equal to 1 multiplied by 1, which is just 1. So if you substitute these values in, this term becomes 1 plus 0.08 to the exponent 1. Multiplying that out, you get 1.08. Okay, now what that means is, remember when you do this multiplier, the 1.08 means you're earning, from our previous lecture solving for I, you had to subtract 1 off. This means that you're earning 0.08 or 8%. Okay? The reason I subtract 1 off is, remember, the multiplier has to be greater than 1 if you're earning interest on it, because if it's less than 1, that means you're losing money, right? Because you're multiplying the amount you started with in your investment by a number that's less than 1, which means it's going to be smaller. Okay, so that's why you have to subtract the 1 off. Now let's look at a second example of quarterly. Okay, so if it's quarterly, again, J is 0.08, nominal interest rate, that hasn't changed, but your M is actually equal to 4 because it's quarterly. So your periodic interest rate is equal to 0.08 divided by 4, or 0.02. Your total number of compounding periods, N, is equal to 1 year multiplied by 4 compounding periods per year, which is 4. So if you substitute them into the equation 1 plus I to the exponent n, you get 1 plus 0.02 to the exponent 4. So if you calculate that out, you get 1.0824. So you can see here, see, this was 1.08, this is 1.0824. So if you subtract 1 off that, okay, again, and that's taking into account that aspect of 1 plus I in the multiplier, you get 0.0824. And if you wanted to convert that to a percent, multiply it by 100 and get 8.24%. So you can see the effective rate is higher, or in other words, you're earning slightly more interest than if it's annually. Okay, so 8% versus 8.24%. Our third example, let's look at monthly. All right, again, J is 0.08, but M in this case is 12, right? Because you're compounding monthly. So if you do your periodic interest rate, J over M, that's 0.08 divided by 12, which gives you a repeating decimal of 0.0066, and it repeats. All right? Your number of compounding periods, total number, N, in this case, it's 1 year multiplied by 12 compounding periods per year. So N is 12. So now your term, 1 plus I to the exponent N, becomes 1 plus 0.0066 repeating decimal to the exponent N, which is 12. So if you calculate this out, you actually get an answer of 1.083. So again, it's slightly larger, 1.08 to 1.0824 to 1.083. So if you subtract 1 off to get just your interest rate, you get 0.083. And if you want to convert that to a percentage, you multiply by 100%, and you get 8.3%. So you see here, it's higher. So what this is showing is an effective rate depending on the number of compounding periods, to show you that the more often it's compounded, the more often it's worth. And again, looking at this, you might think on first glance, this could have been a little confusing. So again, pause, rewind, watch it again, and look at some of our examples. Okay, I'm going to do a few examples where you can see how I do this for a question. So let's look at an example. Again, we're looking at effective interest rates. Assume you are given the choice between a term deposit paying 7.2% per annum compounded monthly, or an investment certificate paying 7.25% compounded semi-annually. Which item offers the higher rate of return? So again, looking back to when I showed you the previous example, that multiplier, 1 plus I to the n, is the most important part. The higher that number is, okay, looking at your formula, future value is equal to present value times 1 plus I to the n. The higher this number is, the higher your future value will be, right? And if you're comparing two deposits, you'll be comparing the same amount of money that you're placing into an investment. So you want to figure out which one is going to make you more money. So in other words, which one has the higher multiplier, 1 plus I to the exponent n. So let's compare the two options. First one is 7.2% per annum compounded monthly. Okay, so again, 1 plus I to the n. And what do we know? We know that our interest rate is, our nominal interest rate is 7.2%, which equals 7.2 divided by 100, removing the percentage sign, which is equal to 0.072. Our number of compounding periods, m, it said it was monthly, so m is equal to 12. So our periodic interest rate, I, which is j divided by m, is 0.072 divided by 12. And if you calculate that out, you get 0.006. Okay, so our value for n, all right, again, it doesn't matter. For all of these questions, you can just assume, unless it's provided in the question specifically, you can just assume that value is 1, right? Just 1 year. Okay, 1 year is the number of years. So when you're calculating n is equal to the number of years multiplied by the number of interest rate periods per year, or number of compounding periods per year, sorry. So n is equal to 1 multiplied, in this case, by 12, which equals 12, okay? Because we're looking for the higher rate of return, right? We're not looking for a specific number. We're just looking to figure out which multiplier is larger. So you can always assume the number of years in this case, unless provided in the question is 1. So I'm going to substitute all these values in. Okay, so we get 1 plus 0.006, and that's to the exponent 12. So if you plug that into your calculator, you get a value of 1.074424. Keeps going, okay? So let's compare that to the second option, 7.25% per annum compounded semi-annually. Okay, so in your second option, again, I'll start with the equation, 1 plus I to the exponent n. J, your nominal interest rate, is 7.25%, which is equal to 7.25 divided by 100, removing the percentage sign, or 0.0725. In this case, it's compounded semi-annually, so your number of compounding periods per year, m, is 2. So your periodic interest rate, I, which is j divided by m, is 0.0725 divided by 2. If you calculate that out, you get 0.03625. Lastly, our number of compounding periods, total number. Again, assume the number of years is 1, unless it's provided in the question. So n is equal to the number of years multiplied by the number of compounding periods per year. In this case, 1 year multiplied by 2, which gives you an answer of 2. So if you substitute these values in, you get 1, plus 0.03625 to the exponent 2, which gives you a value of 1.073814, and it keeps going. So what you're comparing, okay, is your multiplier. In this case, the term deposit, the first item, this multiplier is larger. That means you're going to make more money, or you have a higher rate of return. So in other words, once you compare those two numbers, you write, therefore, the term deposit provides the higher rate of return. Okay? Make sure, rather than just circling one or in an answer, you got to make sure you write which one is actually more, provides the higher rate of return. Let's look at a second example. Ariel has $1,000 to invest and must make a choice between 3.6% compounded monthly and 3.6% compounded semi-annually. Which investment is better and by how much? So again, looking at our formula, okay, future value is equal to the present value times 1 plus the periodic interest rate to the exponent n. The multiplier we care about is the 1 plus I to the n term. So the fact that she has $1,000 in terms of what the question is asking actually doesn't mean anything in this question. But anyways, let's take a look at the question in general. So again, the key item we're looking at is which multiplier is higher, right? Because that means if whatever one has the higher 1 plus I to the n term, means that it actually is giving a higher rate of return. So for the first one, it's 3.6% compounded monthly. So that means that J, the nominal interest rate, is 3.6%, which is 3.6 divided by 100, removing the percentage sign, which is 0.036. M is equal to 12 because it's compounded monthly. So your periodic interest rate is equal to J divided by M, or 0.036 divided by 12. And if you calculate that out, you get 0.003. Again, because in this question I didn't provide you a number of years, just assume that number of years is equal to 1. So that means n is equal to the number of years multiplied by the number of compounding periods per year. In this case, 1 multiplied by 12, which gives you 12. So we want to figure out which one has the bigger multiplier. So we substitute these values in to the multiplier 1 plus I to the exponent n, and we get 1 plus 0.003 to the exponent 12. So this one, multiplying that out, comes out to 1.0366. Okay? The second one is 3.6% compounded semi-annually. So again, our formula that we're looking at is 1 plus I to the exponent n. Our nominal interest rate again is 3.6%, which is equal to 3.6 divided by 100, removing the percentage sign, or 0.036. Our number of compounding periods, m, is equal to 2 because it's semi-annually. Our periodic interest rate, I, is j divided by m, which is 0.036 divided by 2, which is equal to 0.018. Now again, we assume the number of years is 1, so n is equal to the number of years multiplied by m, the total number of compounding periods per year. So n is equal to 1 multiplied by 2, which gives you 2. So substituting those values into our equation, we have 1 plus 0.018 all to the exponent 2. And if you calculate that out, you get 1.03634. All right? So what that means, if you want to compare the two, this number is clearly higher, but how much is it higher by, right? Because it said by how much. So if you subtract one from the other, 1.0366 minus 1.03634, just to see how much bigger it is, you get an answer of 0.000276. Okay, that's actually a percentage, or that actually can be converted to a percentage. So if you multiply that by 100%, you get 0.0276% difference. So it's very minimal, all right, comparing to those two. And this is comparing over a 1-year period. But if you're talking 10, 15, 20 years, a long-term investment strategy, that little bit goes a very long way as it's compounded for years and years and years. All right. Let's look at a third example of this before we move to a different topic. Determine the effective rate of interest corresponding to 9% per annum, compounded annually, semi-annually, quarterly, and monthly. Okay, so there's 4 calculations that we're going to do here. Okay, and remember, we're looking for the effective rate of interest. all right? So we're going to get that multiplier, okay? Let's say it's 1.09. And in order to find the interest rate, we have to subtract 1 off of it. So in this case, we'd get 0.09. And then multiply that by 100% to get a percentage, so it's 9%. Okay? Remember, the multiplier has to be greater than 1 because you're investing and earning interest. If you're multiplying by a number less than 1, that means that $500 multiplied by a number less than 1 would not be worth $500, be worth less, right? And you know that it has to be worth more. So the 1 is kind of like the baseline, all right? So we've got 4 different calculations here, okay? We've got annually. We'll start with item A, annually. So 1 plus I to the exponent n. And if it's annually, we have j, which is equal to 9%, which is 9 divided by 100, removing the percentage sign, or 0.09. That is consistent for all 4, A, B, C, and D, right? Because that's the number that was provided. M, it's annually, so it's just 1, which means I, which is j divided by m, is 0.09 divided by 1, or just 0.09. Now again, I didn't give you a number of years, so assume that number of years is 1, all right? So n is equal to the number of years times m, or in other words, in this question, 1 times 1, which just equals 1. So if we substitute these values in, we get 1 plus 0.09, all to the exponent 1, which gives you 1.09. So converting this to a percentage, we have to first subtract 1, so we get 0.09. Then multiply it by 100%, because right now it's a decimal, right? It has to be a decimal when we place it into a formula. Converting it back to a percentage, we get 9%. Let's look now at semi-annually. So I'll say B, okay, and we're looking at 1 plus I. Again, we're always looking at this multiplier. So semi-annually, J is the same, 0.09. M, in this case, is equal to 2, right, because it's semi-annually. So I is 0.09 divided by 2 to 0.045. N, okay, again, we're assuming it's 1 year, so we have 1 year multiplied by the number of compounding periods per year, which is 2, so we get a value of 2. Substituting that in, we get 1 plus 0.045, all to the exponent 2. So we get 1.092025. And again, if we want to convert that to the actual interest rate, first we have to subtract 1. So we get 0.092025. Then, to convert it to a percentage, you multiply it by 100%, and you get 9.2025%. Okay, item C, quarterly. Okay, again, we're starting with 1 plus I to the exponent n. J is the same, 0.09. M in this case is quarterly, so it's 4, which gives I of 0.09 divided by 2, divided by 4, because our number of compounding periods is 4 this time, which is 0.0225. So now our number of compounding periods, n, is equal to 1 multiplied by 4, which gives us 4. So substituting these values in, we get 1 plus 0.0225 to the exponent 4. And we get 1.09308. Okay, again, converting that to the effective interest rate, we have to subtract the 1 off. So we get 0.09308. Then we have to multiply it by 100% to turn it into a decimal. And if we do that, we get 9.308%. Okay, you can see how it gets higher each time as we've added more and more and more compounding periods. So I ran out of space, so I'm not going to show you D, but I did provide you with the answer here at the bottom. If you do have questions on that one, you can just ask me. All right. The next item I want to look at is equivalent interest rates. Okay, so we looked at effective interest rates and we saw that as you increase the number of compounding periods, your effective interest rate was higher. So now what we want to look at is, again, we're going to look at the 1 plus I to the exponent n term. But for equivalent rates, what that means is this multiplier, it has to be equal for both rates in order for them to truly be equivalent. So in other words, when you're trying to figure out equivalent rates, okay, you have to set those two equations equal. 1 plus the periodic interest rate for the first scenario, the exponent n, or the number of compounding periods for that scenario, has to be equal to 1 plus I, or the interest rate for the second scenario, the periodic interest rate I, raised to the exponent n2, or the number of compounding periods for that second scenario. Okay, so I'm going to show you how to derive a formula to solve for just I, right? Because we're looking for interest rates, right? So we want to know what that second rate has to be in order for these to be equivalent. Again, it's buried in these brackets with exponents. So going back to our last lecture, you're going to have to, again, follow me as I use fractional exponents, right, that we used in our last lesson to solve for this interest rate. Okay, so again, I'm not expecting you to be able to derive this on your own. All right, I'm not expecting you to do that. I just want you to follow this, and it may be confusing the first time you're going through it or the second time you're going through it, but as you start to go through specifically this slide and listen to how I derive it, and then start going through questions, you'll start to understand kind of what I'm saying and what this formula means. So we start with our equation, right? That interest for the first scenario has to be equal to the second scenario, and that all comes down to this multiplier, 1 plus I to the exponent n for the first scenario. So I've used this subscript of 1. Has to be equal to 1 plus I to the exponent n for the second scenario. So I've used the subscript 2. So we want to solve for this second interest rate. All right. So our first step is we need to remove this n2 exponent. And you do that by using the root sign, okay, to the exponent n2. And remember, I didn't write this from the last one, but just remember that if you have a, the exponent 1 over n, that's the same as n, nth root, the nth order root of the value of a. Okay, so I'm applying that same principle to go from here to here. Okay, so I'm rewriting these using this, okay, using what we know. So what this becomes is everything under the root sign, 1 plus I1 to the exponent n1, and then you have to divide it by n2, right, the second term, right, because it's 1 over n. And the same thing applies for the second side, right? So in this instance, 1 plus I2 to the exponent n2, then you have to divide it by n2, right? It places this value into the denominator here. So just like when we talked about in the past, these cancel. N2 divided by n2 just becomes 1. So we're left with just 1 plus I2 on the right side. So now I2 is free, it's out of its brackets, it's ready, so we can solve for it. So now we have a 1 plus I2 on the right side, and on the left side, we have 1 plus I1, or the interest rate in the first scenario, to the exponent n1 divided by n2. Number of compounding periods in the first scenario divided by the number of compounding periods in the second scenario. So to solve for I2, we have this 1 on the right side we have to get rid of, so we just subtract 1 from both sides. So 1 minus 1 cancels, And we're left with just I2 is equal to 1 plus I1, or the interest rate in the first scenario, to the exponent n1 over n2 minus 1. You see again here we have a minus 1. Just like we did in effective interest rates, we have to subtract that value of 1 off, so we get just the interest rate, okay? Not that 1 that is the multiplier, to make sure that your calculation is a number greater than 1, so that when you're multiplying your present value by a multiplier, it actually gives you a larger value, okay, instead of a smaller value. So let's take a look at a few examples. I have 3 examples to show you, which will be the end of this lecture. So now that we have the formula for the second interest rate, let's look at trying to solving. Find the nominal interest rate compounded semi-annually that is equivalent to an annual rate of 6% compounded annually. Okay, so let's start with the formula. I2 is equal to 1 plus I1 to the exponent n1 over n2 minus 1. So one thing to note in this question, it asks for the nominal rate. These are periodic interest rates, and then we'll then have to use the formula I equals j over m to convert it and solve for the value of j, the nominal rate. Okay? So let's look at, I'll just erase this for now, save us some room. Let's look at what we know. Okay, so we know that in our first case, our nominal interest rate, call it J1, is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. We know that M, for the first one, the number of compounding periods, is annually, right? So M1 is 1. So our value for I1 is J1 divided by M1. These subscripts are just to help you see that it's the first case for each one of them. Just 0.06 divided by 1, or just 0.06. Our number of compounding periods for the first one, remember, I didn't give it in the question, so assume that the number of years is 1. So n is equal to the number of years multiplied by the number of compounding periods per year. Both these are for the first scenario. And you know in this question, the number of years is 1 and the number of compounding periods is 1. So this value is just 1. The last item we need here is we actually need the number of compounding periods for the second scenario, or N2. So again, the number of years is 1. All right, and in the second case, it's semi-annually, which means our number of compounding periods per year is 2. Whoops, so we get a value for N2 of 2. So if we substitute all of these values in now, I2 is equal to 1 plus 0.06. That's the exponent 1 over 2 minus 1. So if you substitute all those values in and solve, right, you get a periodic interest rate for the second scenario of 0.02956. Remember, you have to convert this to a percentage times 100%. So you get your periodic interest rate is 2.956%. Now remember, that's periodic. The question asked for the nominal interest rate. So we know that the periodic interest rate is equal to the nominal interest rate divided by the number of compounding periods per year. So 2.956% has to equal the nominal interest rate, J2, divided by 2, which is the number of compounding periods per year for the second scenario, remember, semi-annually. So to solve for this, we need to remove the 2 from the right-hand side of the equation. We do that by multiplying both sides by 2. And if we do that, okay, we get J2 is equal to 5.912%. So if you stop and think about this question, well, does that make sense? Yeah, because your first one started with 6% and it was compounded annually, and you want to find an equivalent rate. Well, the second case is semi-annually, so it has higher amount of compounding periods, meaning its nominal interest rate would be a little bit less, right? Because you're actually earning more interest rate in terms of the effective interest rate, the topic we just talked about. Okay? So let's look at a second example. What nominal annual rate compounded quarterly is equivalent to 8.4% per annum compounded monthly? So, same formula applies. I2 is equal to 1 plus I1 to the exponent n1 over n2 minus 1. All right? So we need to figure out what we know. Well, the first scenario, the scenario that we're trying to compare to, we know that the nominal interest rate is 8.4%, which is equal to 8.4 divided by 100, removing the percentage sign, which is equal to 0.084. Our number of compounding periods for the first scenario, M1, is equal to 12 because it was provided as monthly, right? That means our periodic interest rate for the first scenario is equal to J over M. Again, I use the subscript 1 to denote the first scenario, which is 0.084 divided by 12, which is equal to 0.007. Okay? Lastly, we need our number of compounding periods. Again, remember the formula, we're going to need a number of compounding periods for both. I did not provide it in the question, like I said, so number of years is equal to 1. So N1, okay, number of years multiplied by the number of compounding periods per year is equal to 1 times 12, which is equal to 12. N2, okay, again, our number of years is 1, and the second one was quarterly, so we know that it's multiplied by 4. So our number of compounding periods for the second scenario is 4. So now let's substitute these values into the equation. We get I2 is equal to 1 plus 0.007 to the exponent 4 divided by 12. Oh, that's backwards actually. 12 divided by 4 because N1 is 12 and N2 is 4 minus 1. So if you do that, you get that I2 is equal to 0.021147, it keeps going, okay? And if you're converting that to a percentage, you get a periodic interest rate of 2.115%. Again, I'm rounding that. All right, so that's a periodic interest rate. It asked for a nominal rate. So remember, periodic interest rate is equal to the nominal interest rate divided by the number of compounding periods per year. So that means the 2.115% that we calculated is equal to the nominal interest rate divided by 4, because this one is compounded quarterly. So to solve for this, we have to remove the 4 by multiplying both sides by 4. And if we do that, these 4's cancel, and we get our nominal interest rate is 8.46%. Okay? You can see my answer was 8.459. The only difference there was because of rounding. So let's look at a third and final example. Roy's Bank currently offers 2.4% per annum compounded semi-annually savings accounts. What is the nominal rate compounded monthly that would be equal to his semi-annual rate? So again, we're looking for a nominal rate. So once we calculate this periodic rate I, we're going to have to convert it to a nominal rate. But first, let's start with the formula. I2 is equal to 1 plus I1 to the exponent n1 over n2 minus 1. So our nominal interest rate in the first scenario, J, 2.4%. Number of compounding periods, it's provided as semi-annually, which means M is 2. So our periodic interest rate, I1, is equal to J1 over M1, which is 2.4%, actually 2.4% divided by 2, which is 1.2%. This time, just as I was doing the question, I didn't convert the interest rate first, but now you can convert it to a decimal. which is equal to 1.2 divided by 100, removing the percentage sign, which is 0.012. Okay? I didn't convert the nominal interest rate as a start to a decimal. Like I said, I usually do, but you can do it either way. So now the last times we needed the number of compounding periods for both scenarios. Again, I didn't provide you a number of years, so assume it's 1. So first one, N1 is equal to the number of years multiplied by the number of compounding periods per year, M1, which is equal to 1 times 2, which is equal to 2. Okay? Your second scenario, N2, it gives you that it's compounded monthly. So that means it's 1 year multiplied by 12, which gives you an answer of 12. So you can substitute all these values into this equation. So I2 is equal to 1 plus 0.012. And that's the exponent N1, which is 2, divided by N2, which is 12, minus 1. If you calculate this out, you get I2 is actually equal to 0.00199. Okay, converting that to a percentage, right, times 100, you will actually get a value of 0.2%. That's just rounding it, okay? So again, this is a periodic interest rate. We have to convert it to a nominal interest rate. So we know periodic interest rate is equal to the nominal interest rate divided by the number of compounding periods per year. So we know 0.2% is equal to J2 divided by 12, because our number of compounding periods in this case is monthly. So to solve for this, we have to multiply both sides by 12 to remove that 12 from the denominator. So those 12s cancel. And we get a nominal interest rate J2 of 2.4%. Again, you'll notice my answer of 2.388%. That's just the difference being rounding, showing more steps while we do the problem together. Okay? So this is the last section after this first unit, the last topic that we're going to cover. Again, if you have questions on this, feel free to send me an email. If you have questions on your assignment, feel free to send me an email. And if not, I'll talk to you on our next tutorial. Thanks.